Again, when we last left off yesterday in 3.3, our very last question that we're asked on the previous page asked you to calculate out the residual value and talk about what that actually means. So we need to actually define what a residual is. Okay. So we not only have the definition up here, but we have a picture that helps you visualize what a residual is talking about. What happens for a residual is you're taking your line of best fit, your least squared regression equation that we were finding a little bit yesterday on our calculator even, this y hat equals a plus bx. And sometimes we ask you to even graph it on your scatter plot. What happens is some of your points are nice and close to the line, and some of your points are farther away. Some are above, some are below. What we want to take a look at is how close or how far are all of those values away from the predicted value. That is what's called a residual. This distance is a residual. Because what you're doing here is you're going to compare your observed y, so the value you get from your data, and you're going to subtract it, or subtract from it, the predicted y. Otherwise known as y hat. That distance is what we call the residual. It's basically how far off are we from our observe and predict. How much of you could almost say, how much off were we from predicting the observed value? So what happens is sometimes your residuals will be positive value. Observed minus predicted. If your observed is above your line of best fit, it's a positive residual. Sometimes you get a negative residual. Okay? That would just mean your observed value is below your regression line. So, to find this value and to understand what it means, turn back one page and let's go back to the Hot Wheel experiment that we were doing on Wednesday. Okay. On Wednesday, we did this Hot Wheel experiment and got our regression equation down here. Okay. So here's our regression equation. And in this question it says, what's the value of the residual at a ramp height of 4 feet? Right here is our predicted value. We found this predicted value simply by taking 4 feet, plugging it into our equation, and figuring out what our equation would say the car should jump based off that equation. We said that it should jump 33.23 inches. The question becomes, what did we actually observe? So, we go back up top to the top of the data, and we look at the observed value of 4 feet. And we see that, well, when we actually did it, the Hot Wheel car jumped 32 inches. Okay. So when we calculate out this residual, just going to move this up here, there we go. Our residual is simply equal to our observed value minus our predicted value. So our observed value, this is coming right from the table up top, was 32. Our predicted value, that's what we got from our equation, 33.23. When we subtract them, we get negative 1.23 inches. Okay, so our units still stay what our y value represents. Okay? So this is the distance that it jumped. Now the question, what does this negative 1.23 actually represent? Okay? Well, what it means is our predicted value or our predicted jump distance was 1.23 inches more than what was observed at a ramp height of 4 feet. So the residual basically now we'll start to take a look at how off is my line at any given x value. Sometimes it's going to be off above it or below it. This time, okay, our predicted jump distance was above it because my residual was negative. My observed value was below the predicted value. So being able to interpret residuals is very important. Later on in this course, what we'll also do is we'll start to take a look at, I believe this is actually tomorrow, we'll talk about the residual error, okay, or what was the average error for all points. That's coming up tomorrow.
Tomorrow?
Or
Saturday?
Monday.
I won't be tomorrow.
Alright, so now, just to let you know and talk a little bit more in greater detail, we've been just using a regression equation, and on our calculator, we have actually been calculating this out on our calculator. So when we go stat, we use the right arrow, and we choose number 8, which is that ln reg a plus bx on our calculator. We're actually calculating out the line of best fit. And it's technically called the least squared regression line. You'll see this abbreviation, LSRL, in your textbook. And sometimes they'll replace it with from an L to an E down here, where the only difference is line versus equation. Okay? So when you see that symbol notation, don't freak out. Just know that it represents your least square regression line or equation if it's using L versus E. Now, what can happen is sometimes you can actually calculate out this particular equation without having the actual data points, but if you actually have some summary data, you can actually calculate it out.
There's a ghost.
Yes, I know the lights are flickering in the back there. So,
It's October.
it is October. That means Halloween's fast approaching. So, again, our prediction equation, y hat equals a plus bx. Y hat represents the predicted value, b is your slope, a is your y-intercept. So if you want to find the equation from some summary statistics, you have to have certain summary statistics to find it. You can find your slope and your y-intercept using these two formulas. First of all, what do the formulas require? Well, you need to have the summary statistics of the mean of x and the standard deviation of x. You have to have the mean of y and the standard deviation of y. And the other thing you need to have is the correlation coefficient, r. If you have those 5 pieces, you can find the least squared regression equation. The slope can be found by taking that correlation coefficient and multiplying it by the standard deviation of y divided by the standard deviation of x. If you think about what slope actually represents, change of y over change of x. Okay? So what happens is we know that correlation gives us our direction. That correlation coefficient tells us positive or negative. Okay? Standard deviation is a measurement of distance, so it's always going to be positive. So the r is going to take into account whether our line is positive or negative. But it's not just equal to the slope. since we're talking about change of y and change of x, and we're talking about a measurement of spread, and what is that average distance, you divide by the standard deviation of y over the standard deviation of x. Change in y over change of x. Now, once you have your slope, so when you do these problems, this is the first piece that you need to find. Because really, if you want your equation, you just need to find slope, you just need to find y-intercept. Once you have your slope, right, you need to find your y-intercept. Now, to do that, basically you're trying to get a by itself. So I can take this part of the formula and move it to the other side. If I do that, I'd have y hat minus bx equals a. But one of the things I know, okay, from yesterday when graphing our least squared regression line, what's one of the points that the least squared regression line goes through? Remember this from yesterday? Or sorry, for Wednesday? I go back here, when I was graphing it, what points do we use to graph? Okay, and what is that point?
The mean point.
The mean of what? The mean of x, mean of y. It's that coordinate. It's that simple. So now, what I can do is go back here is say, all right, here's my equation. I know a point that's on the line. I can plug those values in here. Replace y hat with the mean of y. Replace x with the mean of x. Those are actual values that I have. I can put all those numbers here and I get a. So you can see you can get a all by itself. Okay. All right, so to show this in practice, okay, flip to the next page and we're actually going to start with number 2 first. And then we'll go back up to number 1. How many of you ever look for used cars online? Anybody? You did one time, so we got maybe 1 or 2 people that have ever looked. Okay, so a few of you, what sites do you use? Car Soup? Craigslist? Okay, Craigslist, Car Soup. And they're like CarMax, isn't that another one that's on commercial? Okay. So, anyway, when you're looking online at different prices of cars, sometimes you'll be looking at a specific make and model. For instance, I drive a Honda Accord. I've been driving Honda Accords for over 20 years now in my life. I love those cars. I've always liked them. Okay, I'm a dedicated Honda Accord driver. Okay? So, if I were to look up Honda Accords, for instance, say if I wanted to buy a used 2005 Honda Accord, right? I could get all sorts of different values, price values for 2005 Honda Accords. Same make and model, okay? But what's one of the things that changes the price drastically?
The trims.
Okay? But say the trim is exactly the same. Same trim, okay? But probably the biggest key is mileage. The more miles on the car, usually it's going to be cheaper, okay? That's what this problem is kind of driving at here. So, we look at what number 2 is talking about here. It says, the number of miles in thousands of miles for 11 used Honda CR-Vs, so someone looked up 11 of them, have a mean of 50.5, which is really 50,500 miles, and a standard deviation of 19.3 thousand miles. The advertised price for those same 11 CR-Vs has a mean of $14,425 and a standard deviation of $18,900 or $99. Sorry. Correlation for these variables is negative 0.872. A says find the equation of the least square regression equation that would be used to predict the advertised cost of the Honda CR-V when knowing how many miles are on it. Now there's a lot of information going on here. So one of probably the most important things to do with this problem is figure out which is X and what is Y. So if I go to this part here, it says predict the advertised cost of a Honda CR-V. So I like to draw a little X, Y axis over here, and I'm going to write the cost, or you could also think of it as the price. So I know my predicted Y value deals with the cost. Okay? So if it helps you, some of you might prefer to say Y is the predicted cost of a Honda CR-V. How am I predicting that cost? Knowing how many miles are on it. So here are going to be the miles in thousands. So it's good to know that we're in thousands of miles. So I'm going to write X is basically the mileage of the Honda CR-V. Good to know. I mean, I'm thinking to myself, this would actually be kind of nice to have this equation so you can start to see who is actually potentially, by the prediction line, overpricing their car and underpricing their car. Now, of course, there could be other factors and variables on the price, but if we're solely looking at mileage, it'd be kind of nice to know this. So, we want to find the equation. So, in order to find the equation, boy, I'm going to need to know what's the mean of X. What's the standard deviation of X? I'm going to need to know what's the mean of Y. What's the standard deviation of Y? And do they give me my R? So, since X is mileage, did they tell me the mean miles driven? And the standard deviation? So 50.5, standard deviation 19.3. So then the cost or the price, $14,425, $18.99. They do give us R, negative 0.874. So I got to make sure I have all those 5 values to figure out this equation. So on my other page with my slope, that's what I want to find first. I want to find B. That is your correlation coefficient times your standard deviation of Y divided by the standard deviation of X. So my slope, negative 0.874, standard deviation of Y, 14,425 over 1899. Did I screw those up?
Yeah.
I feel like I flipped those around. I really screwed them up. My apologies. Let's do this. I'm picking the wrong values. I got to pick standard deviation, Mr. Bartz. Standard deviation of Y is, 1899. Standard deviation of X is 19.3. Glad I caught that now. So R, standard deviation of Y, standard deviation of X. So, calculator time. So we'll pull that up real quick and let's multiply and calculate that out. Negative 0.874 times 1899 divided by 19.3. Negative 85.996. Since we're talking about a price here, negative, let's round it. It rounds actually nicely to the nearest penny of negative 86. So if we think about slope in the context of the problem, for each additional 1,000 miles, the predicted cost of a Honda CR-V goes down by $86. That seems fair and correct. All right, so now we want to find A. A is found by going the mean of y minus your slope times the mean of x. So A equals 14,425 minus a negative 86 times the mean of x, 50.5. Calculator time yet once again. 14,425 minus negative 86 times 50.5. Wow, 18,768. Meaning a used CR-V with no miles on it, which sounds interesting, but maybe it's just a 3-year-old car that no one ever drove, should be worth $18,768. So now we just put those two together for our equation. So y hat equals A, which is 18,768 minus 86x. Beautiful.
Yes.
All right, question B. It says explain what change in price we would expect for each 10,000 miles. So if we're talking about a change in price, we're talking about the slope. So we're really just focusing on negative 86 times x, where x represents, again, the number of miles in thousands. So what am I going to replace x actually with? What number? Okay, we're going to replace it with just 10, not 10,000, but just 10, because our x is representing in thousands already. So we get negative 860. So what does that actually mean in this context? So for each additional 10,000 miles, what? You got it. So for each additional 10,000 miles, the cost of a Honda CR-V decreases by $860. Just out of curiosity, do any of your families lease a car? Do you know? We have one? Okay, just only one? Or we just don't know for sure? Okay. I actually have my first lease car, so, but, you know, on the leases, do you have a set mileage, do you know, that your parents can go? Do you even happen to know what it is, do you?
No, my mom always goes over it.
Okay, so your mom always goes over it. So, like for my car that I have leased right now, I can only go 12,000 miles a year, which is basically 1,000 miles a month. So if I go over that, I have to pay 15 cents a mile, okay? So here, 10,000 miles decreases the value by $860. Be interesting to see, well, what's 15 cents times $10,000? $1,500. That's how much the car company is gonna cost me. or charge me, but I have an Accord versus a CRV. I don't know if that changes. But it's interesting how they do that. All right, questions right now with number 2. Let's go back to number 1 and just practice finding and interpreting a residual. So, number 1 says the equation of the least squared regression line for sprint time and long jump distance data is given to you right there. So we actually just give you the equation. It says find and interpret the residual for a student who has a sprint time of 8.1 seconds. Okay? So, in order to first of all find your residual, we need to figure out the observed value minus the predicted value. So again, observed y minus predicted y. We know the sprint time that we're looking for is 8.1 seconds. So that's my x value. So what is my y value? Not y hat, but what's my y value? Do we know it? Can we find it somewhere? Where is it? Yeah, on the table. So this is x. Here's my observed y. So right now for my residual, I know that y is 151. However, I still need to get the predicted y. Well, do they give me a way to get predicted y? Yeah, they give you what? They give you the equation 304.56 minus 27.63. And guess what I replace x with? 8.1. So, calculator time. So, 304.56 minus 27.63 times 8.1. 80.76. So if I subtract that, 80.76, my residual equals, I think, 70.24. So now the question is, what does that mean in this context of the problem? So what I like to tell students to do is sometimes, if it helps you, visualize what your residual actually is. If this is your y hat equation, and this was 8.1 seconds, the observed value is much higher than the predicted value by this distance of 70.24. In this case, it's in inches. So we could say something to the extent of this. Our predicted value for a sprint time of 8.1 seconds was 70.24 inches higher than what was observed. Now, with residuals and how you interpret them, there's two correct ways you could actually interpret this. I started by saying our predicted value. You could say our observed value for a sprint time of 8.1 seconds was 70.24 inches lower than what was observed. So you can flip them around. You just have, when you describe, you can't just say higher in both cases. It's actually lower if I flip them around. That's why I find drawing a picture helps you see, should I be using higher or lower for which value I put first versus second, because it does make a difference. All right, questions? Hey, wow, look at that. I got done with the notes in a almost record time here. That's not too bad for me.
Totally.